Hello and welcome. Today we're going to address heat and thermodynamics. So this section of our learning for this year, this deals with AKS 15, which states that we're going to relate the effects of thermal energy to kinetic molecular theory. Might sound a little complex, but let's kind of analyze the objective and break it down. So thermal energy is what we're really looking at. And when we speak about kinetic molecular theory, what we're addressing with that is the idea that molecules are moving. And if we look at how fast they're moving, that's going to reveal to us what thermal energy is. So this is something that you've seen earlier in the year. What we have here is we have essentially the temperature of the substance, and this is the amount of energy that we add to it. And we can see that with lower temperatures, we're going to have solids, sometimes liquids, but definitely solids are at the lowest part of the temperature scale on the y-axis. As we add energy, you can see that two things can occur. You can either increase the temperature, or you can increase, or you can actually cause a state change. So if we go from solid to liquid or liquid to gas, that's a state change. When that occurs, there is actually no temperature increase. So with this line being perfectly horizontal, there is no temperature increase, but rather that energy that you add through heat, or adding thermal energy, is going to cause it to change state rather than increase temperature. Another example, we looked at this earlier in the year as well, and with this phase diagram, we see the triple point. We can also see we have solid, liquid, and gas, or vapor, as it says here. Two ways to cause that state change, if you remember. The first is we can manipulate pressure by either increasing the pressure or decreasing the pressure. But the second way was temperature. And when we say temperature, we are really referring to heat and thermal energy. So looking at that term thermodynamics, it sounds like a cool word, but if you were to analyze it and look at the parts of the word and what those parts mean, thermo reveals, heat or thermal energy, how hot or cold something is. And then dynamics, that word simply means movement. So when we speak about thermodynamics, what we are referring to is the movement of heat, or it would be better to say the movement of thermal energy. So a term that we use a lot is temperature. When you see the term temperature, what you need to think about is that temperature is the average kinetic energy of the particles in an object. So any object, if you were to hold, let's say, this cup of hot chocolate. So with this cup, the particles that make up the hot chocolate inside, they are moving. And if they're hot, they're moving faster. If they're cold, they're moving slower. But the idea is each particle is moving at a unique speed. But the overall average is what I'm concerned about when I look at temperature and being able to describe that to someone else. So again, that's the average kinetic energy of the particles in the substance or an object. Now, one idea that's important for us to understand and remember is that when things get warmer, when their heat increases, they're actually going to expand. They're going to spread out. They need more room to move. So, a cold cup of milk, well, that's a bad example. A cold cup of hot chocolate is actually going to have less volume than a hot cup of hot chocolate. And the idea is that they're going to move away from each other as they're moving faster. Now, by contrast, when things get colder, when they cool down, they're actually going to contract or come closer together. Now, you'll see this when you look at bridges. If you're driving around in your car and you see a bridge that has some kind of a metal joint or a separation in it, that's built on purpose because when the weather gets cold, is going to contract. When the weather gets warmer, it's going to expand, and you don't want that bridge cracking and breaking apart. So you have those joints that are built into it to ensure that that will not happen. So we have a few laws when we talk about thermodynamics. There are three important things to remember. First of all, the first part of the law of thermodynamics refers to the conservation of energy. Energy is never created nor destroyed. It always has to go somewhere. It has to come from somewhere. The second law of thermodynamics states that heat moves from a high concentration to a low concentration. Now, essentially what that means is moving from hot to cold. If I hold this hot cup of hot chocolate, and my hand is, average body temperature, but the hot chocolate is actually very hot. That's why the cup has a built-in handle, so I can hold it on its side and not have to experience all that heat coming out. But if I were to place my hand on the side, then I could feel the heat coming out of the cup into my hand. And essentially, it's moving from an area where it's very hot to where it's cooler. So, the opposite's not going to hold true. Now, if I had a cup of ice here, if I had a glass that had ice water in it, it would feel cold to me because the heat would be leaving my hand and going into the glass of ice water. Here, the opposite is happening. The extremely hot chocolate is sending its energy into my hand. So it's where it's concentrated to where there's not that much of it. That's exactly how thermodynamics works. It goes along that concentration gradient. Think about a wheel rolling down a hill. Same concept. You have that high concentration or high elevation moving to a lower concentration or lower elevation. Now the third part is that everything is slowly moving towards absolute zero. Absolute zero is 0 degrees Kelvin, and that is where all molecular motion stops. Everything in the universe is the same exact temperature, and we're going to talk more about that later on. But these are the three laws of thermodynamics, and really, in all honesty, these things are based on common sense, and they're very related to each other as well. So, looking at that word heat, we use that word a lot. We use it in a way that's not exactly accurate. But if we want to be precise, the definition of heat is thermal energy transferred between two objects that are different temperatures. Alright? So if something is going to feel warm to you, that's because it has more thermal energy than you have. The cup of hot chocolate has more thermal energy than my hand. Therefore, the cup of hot chocolate feels warm to me. Energy is actually leaving the hot chocolate and going into my hand. Now, if something feels cold to you, the opposite is true. It is moving from your hand into the object. So if you were holding a glass of ice water, again, it would feel cold because you're actually losing thermal energy. Okay? So thermal energy is a total kinetic energy of particles that make up a substance. It's going to depend on two things. It's going to depend on the temperature and how much of the substance there is, or mass. So if I had a cup of hot chocolate, even if it's the same temperature of a large, let's say you had a large pot of hot chocolate on your stove, that pot of hot chocolate is going to have more thermal energy even though it's the same temperature as the cup because there's more of it. Now, this is not the best way to describe this, but you could think of it as if you're multiplying mass times temperature. So if things have the same amount of temperature, they have the same exact temperature, if there's more of one substance than the other, it's going to have more thermal energy for that reason alone. And we're going to talk a lot more about that later in a different video. As with all types of energy, we're going to measure thermal energy in joules. Now here's an example. I have three substances here. I have juice, a bottle, and some water. So let's say what I do is I put the juice in the bottle and I put it in ice, in a cooler full of ice. Now over time what you're going to see is that afterwards what's going to happen is So you start out with 25 degrees Celsius for the juice, 25 degrees Celsius for the bottle, and 0 degrees Celsius because that's the temperature of ice. As it sits in that ice, and I'll leave it alone for a very long time, what's going to happen is the energy is going to move out of the juice and the bottle into the ice. What will happen over time is that you're going to have everything the same temperature. Here we have 25 degrees Celsius, 25 degrees Celsius, and 0 degrees Celsius. And then afterwards we have 9 degrees Celsius, 9 degrees Celsius, and 9 degrees Celsius. That's how it works. It distributes itself until it's completely even with everything around it. Now this diagram is really great, and I'll show you this in a better perspective in just a moment. But when we have heat transfer, there are 3 types of heat transfer. So first we have conduction, which is heat transfer essentially through a solid. So if you are holding the hot chocolate in your hand and you touch it, the hot chocolate is heating up the cup, and then the cup heats up your hand. Well, your hand is a solid, the hot chocolate is a solid, so those things are touching. The second thing is called convection, and this is heat transfer by the movement of a liquid or gas. I'm sure we would all agree that hot chocolate is a liquid. So when the hot chocolate is hot, it heats up the side of the cup. Because the heat's moving from the liquid to the cup, we would call that convection. So convection is a heat transfer through the movement of a liquid or a gas. If you steam something, like if you're making some kind of food at home and you steam that, that's also going to be convection, because remember that water vapor is a gas. The last one is kind of neat. It's called radiation. This is a heat transfer that occurs without the use of matter at all. No matter is needed. This is essentially how the sun's energy reaches the earth, is it travels through space. There's no matter outside of our atmosphere, and it comes to earth, and it's the heat transfer through electromagnetic waves or electromagnetic radiation. So we'll talk more about that later in the year as well, but here you can see a diagram that shows you all 3 different types. Let me show you that in a closer perspective here. It's a great illustration. It shows you that here's a metal rod that's being held close to the fire. Basically the fire is heating up the rod, and that's happening through convection. This hot air is rising. This person's hands are being warmed by the hot air rising. The rod, the metal rod, is being warmed by the hot air rising as well. And then this is a solid, so it travels up through conduction to the person holding it. Now, the person holding it was very wise, because you can see there's a glove here. That glove is an insulator. We're going to address that in just a moment. But the insulator prevents heat. It prevents the movement of thermal energy. But here, this is conduction. This is allowing for it to transfer up here, and the rod gets progressively warmer. At the bottom, you can see radiation. Essentially, through electromagnetic waves, they are traveling from the fire to the person's hands. And through that electromagnetic radiation, there is no matter that needs to be used. Here, with convection, you need to have a liquid or a gas. With conduction, you must have a solid. But with radiation, there is no matter needed at all. So looking at conductors and insulators, I'm going to ask you to define these and give some examples. But just to show you a couple of things. The cup, the coffee cup, where I have the hot chocolate. The cup itself is an insulator, and is designed this way because you don't want to have a hot beverage that gets cold very quickly. You might also notice that the stir that I'm using is made of wood. Okay, so wood itself is also an insulator as well. You might notice that a lot of these stirs are made of wood or plastic. Plastic is an insulator as well. If you look on the side of this cup, which I bought this morning, you'll notice that I have one of these cardboard sleeves around the outside of the cup. Well, why would I have that? The coffee itself is very hot, which is a good thing. When you buy coffee, you want it to be hot. But sometimes it's too hot to hold it without the sleeve. And that's because even though this is an insulator, the cup itself, it's not a very good one. And so if you add that cardboard sleeve, it gives you more insulation. Your jacket that you're probably wearing today, because it was kind of chilly this morning, is also an insulator. What it does is it allows you to prevent your energy from your body going out into the air around you. It prevents that from happening. So it stops heat, or it stops the movement of thermal energy. There are also some things that are conductors. Metal is a conductor. If you made a coffee stir out of metal, that would not be a very good idea. That would just burn your hands. A coffee cup, if you made that out of metal, that would not be a good idea either, because that would also burn your hands. But there are instances in our lives when we want things to be conductors and we want things to be insulators. If you're trying to heat something up on the stove, you want that pot or that pan to be made of metal, because you do want the heat to go from the fire beneath or the electrical component from the stove into the pan, into whatever food you're preparing. So there are times when you do want to have conductors and you do want to have insulators. I would not suggest putting hot coffee into a glass. Glass is a conductor of thermal energy, as is metal. Okay? So moving right along. So when we look at the changes of temperatures, okay, we have an idea called thermal conductivity. And that's essentially a way for us to describe the rate at which things are going to conduct thermal energy. Okay? So metals, a glass, other things such as that, similar objects, those things will be very good at conducting thermal energy. So they're going to have a high thermal conductivity rate. Styrofoam, plastic, cloth, paper, cardboard, those things are going to have a very low thermal conductivity. So rather than putting things into a category of conductor or insulator, it's best to say, where they are on that gradient. How much of a conductor are they? Everything is going to conduct a little bit of heat, but it's the things that are worse at it that we want to use as insulators. So you might notice that if you get into your car on a hot summer day and you grab the seat belt, that the metal part of the belt is hot. It can actually burn you, whereas the strap and the plastic are not. Why is that? Well, you might have come to the conclusion that the metal is a conductor of heat, whereas the strap itself is an insulator. So today I have covered the basics of heat and thermodynamics. There's a lot more to discover, and we will reveal that in later videos. Thank you for paying attention.